All right, so the plan for today is to talk about this thing called stoichiometry. And before I get into that specifically, let me just sort of put it in the context of our class. So the cool thing is that we have spent a lot of time talking about the chemistry mole and how we can use the chemistry mole. We've spent a bunch of time talking about writing equations and balancing equations. And those two ideas separately, though you could make an argument they have some place in chemistry, really by themselves they don't make a lot of useful stuff in chemistry. So what we're going to be doing is we're going to be combining a balanced equation with mole conversions, and you'll see that together there is an actual very useful and practical use for this thing which is known as stoichiometry. So before we get into it, let's talk a little bit of review. We're going to review equations really fast. So when I show you this, N2 plus H2 produces NH3. Is this an accurate representation of the reaction going on? If you look at it, you should be like, oh no, because look, there's two N's here and only one N here. So where did that extra N disappear to? There's two H's here, three H's here. Where did that extra H come from? That's a problem. That's this idea of law of conservation. We have to balance it. So what we do is we say, okay, two N's on this side, so if I put a 2 over here, now that's balanced. Now I have 2 times 3, that's 6 H's, so if I put a 3 over here, now that's balanced. That's the law of conservation, saying that matter can be changed. You can make new compounds or new ideas or things like that, but you can never create matter and you can never destroy matter. The atoms that you started with still have to be there somewhere. They can just be changed around. All right, so we've talked about balancing and coefficients and stuff, but we never really talked about that number there having a specific unit. We just think of it as like a number. Well, it turns out that those units are moles. So here's where moles makes an appearance in this thing called stoichiometry. So these are not just random numbers, they're the number of moles of hydrogen for every moles of ammonia and moles of nitrogen. So all of stoichiometry is based on that idea, this mole ratio. So we can use the coefficients that we wrote in a balanced equation to talk about moles in that chemical equation or that chemical reaction. And then because we know about molar mass, then we can convert that into something we can use in lab, and that's what gets so exciting about stoichiometry. All right, so mole ratio is our key thing. Mole ratio is the thing that you have to understand, and it comes from the balanced equation. So let's practice that mole ratio just a little bit. So for example, imagine you have the decomposition, the splitting up of water. So you start with 2H2O, produces 2 hydrogens plus oxygen. Okay, so what this really means is that those numbers are moles. 2 moles of water, 2 moles of hydrogen, 1 mole of oxygen. So remember, when there's no number, that doesn't mean 0, it means that there's really one of them. So let's write those as ratios, mole ratios. So the mole ratio between water and hydrogen, if we look up here, it would be 2 moles of water, and we write it as a ratio, so dot dot, for every 2 moles of hydrogen. So those 2's came from up here. So if this was a different equation, those numbers wouldn't be 2, they'd be something else. How about if we did between water and oxygen? Well, we look up here, 2 in front of water, no number, which really means 1 in front of oxygen. So that would be 2 moles of water for every 1 mole of oxygen. And we can keep doing that. We can do it between any chemical in here. So what about between hydrogen and oxygen? Well, there's a 2 in front of hydrogen, 1 goes with oxygen. So we would say 2 moles of hydrogen for every 1 mole of oxygen. So those are known as our mole ratio. And that's the only thing that makes stoichiometry different than just a regular dimensional analysis problem. So now we can use a balanced equation. So now we know how to write equations, we know how to balance equation. We can use those equations to go from moles of one thing to moles of another thing. And that's what makes it stoichiometry. So when we do that, when we go from moles of one thing to moles of another thing, I refer to that as the switchover step. You're switching chemicals. So the switchover step generally would look like this. You would start with some number of moles of anything. I'm going to call it RV, all right? So you would start with some number. This is my pretend chemical. So then to do the switchover, it's going to look like dimensional analysis. You would need to know moles of RV, and let's say I was converting it to moles of JK. So this would be some number, this would be some other number. And these numbers, so these numbers here, these numbers that are blank, you would fill in using the coefficients from the balanced equation. Balanced equation. All right, you got that. All right, so to get the ratio, you just look at the coefficients. And then after that, it looks like a normal balance or a dimensional analysis problem. So let's take a look at this. So let's say I asked you this kind of a question. 2.6 moles of water, how many moles of oxygen is that? Well, that's a problem that looks like this. We have a starting point, 2.6 moles of water. But I don't want moles of water, I want moles of something else. That means you need to do the switchover step. Well, the switchover step happens when you go from moles to moles. So we can look back at this balanced equation. So we know that there's this much water, this much hydrogen, this much oxygen. So to fill this in, we can say, okay, I'm going from moles of water to moles of oxygen. Moles of water has to cancel, so I'm going to put moles of water on the bottom. Moles of oxygen is what I'm switching to, so there's my switch over, and I fill in the blanks looking at that balanced equation. So if I look back up here, I know that there is 1 that goes with oxygen and 2 that goes with water. So then I can fill in down here 1 mole of oxygen, 2 moles of water. The question, and then moles of water goes away. I'm left with moles of oxygen, which is what it's asking for. So then now I just need to multiply and divide. So 2.6 divided by 2, so either do that in your head or you can use your calculator, ends up being 1.3. And then the label is moles of oxygen because that's the only thing not crossed out. So the only thing that's different here, so in order to make stoichiometry seem not so foreign, is that it's still dimensional analysis. It's just that you fill in your conversion from the coefficients of your balanced equation. Let's try another one. 2.15 moles of hydrogen are produced. How many moles of water did I start with? All right, well, as a chemist, you might be curious about that. So I'm going to start with my 2.15 moles of hydrogen. But then I don't want to know about moles of hydrogen. I want to know how many moles of water did I start with. So that's switching chemicals. Moles of hydrogen I want to get rid of, which means it has to go in the opposite spot always. Moles of water is what I'm trying to switch over to, so that's going to go on the top. I fill in the ratio between these two just by looking back up at that balanced equation. So let's go back up there. 2 moles of water, 2 moles of hydrogen. Okay, so let's fill that in. 2 moles of water, 2 moles of hydrogen. Moles of hydrogen goes away. I'm ready to solve it because it's asking for moles of water. So when I do that, look it. Well, 2 and 2 also cancel. So my answer is 2.15 moles of water. 2.15 moles of water ends up being our answer. That is dimensional analysis with a balanced equation called stoichiometry. So these are the kinds of questions that start to get more useful. However, we can't stop here because as a scientist, moles, we know what they mean, but they're not very useful. So we need to have one more set of things we talk about of how do I turn a problem like this into something a little bit more useful. Well, we can use molar mass. Because remember, molar mass is really just the number of grams in 1 mole. And that comes from the periodic table, remember? So p-totes. You look up the atomic mass, and then you give it the label grams per mole. So that's molar mass. Mole ratio is your number of moles of A equal to number of moles of something else. So different chemicals. So this is a ratio between one chemical to another chemical. Where do you get that from? Well, that's that thing we just learned. That's the balanced equation. So those are our things about stoichiometry. So what you maybe are starting to guess is that instead of stopping at moles, I might use my molar mass to convert this number into grams. That's eventually where I'm leading you with this. So let's think about what this is going to look like then. All right, so before I start to having you do some example problems, there's 3 big things that are going to help you with your stoichiometry. When you have a stoichiometry problem, you always need to have a balanced equation. If you don't have a balanced equation, you're not going to end up with the right mole ratio. You're going to think all the numbers are 1 or that there's some other numbers. So the correct mole ratio. After you have a balanced equation, every stoic problem has that thing called the switchover step. That's where you go from moles of one thing to moles of the other thing, and the units need to be in moles. So if I give you your starting number in moles, you can do the switchover step right away. if I give you a number in grams, you have to get to moles before you can do the switchover step. And remember, the switchover step is that mole ratio like we just practiced. So, like I just said, if the given is not in moles already, you may need to use molar mass or even density to get to moles. Because remember, density equals the number of grams equal to 1 milliliter or liter. So that might help you cancel it. Whereas molar mass, remember, is the number of grams equal to 1 mole. And then remember that this blank you fill in by looking at the periodic table. So you can use that to, so if I gave you a number that started in grams, you could use this number to cancel grams and get to moles, and then you would do switchover step to get to the other chemical. All right, so now we're starting to get into specific enough where it's really just going to be best for you to start doing some practice. So if there's another person that is at the same point as you are, I would like you to work with a partner and do the stoichiometry intro practice, which is basically filling in blanks, kind of like the DA puzzle day where you sort of like figured out how to do dimensional analysis. You're going to use that same process to figure out stoichiometry. All right, go to it. Thanks for listening.